Polynomial and rational functions are some of the functions that are easier to calculate limits with, and that's because we know a lot about linear functions already and we know limit laws. So as an example, if you look at this degree 3 polynomial, you can easily look at it by splitting certain things up and first using the sum law to split this into 4 different limits, right? This last one is very easy. The limit of 1 is just 1. That's a linear function, right? If you graph that, that is just the horizontal line y equals 1 right there. So the limit's going to be 1 regardless, so just put a 1 there. That's second to last limit, ax, is also a linear function. It's ax. This is 1, so y equals 1 and y equals ax. So that means we know the graph of a linear function is a line, so it's easy for us to deduce that the limit of ax as x approaches 2 is just 2 times 8 by direct substitution. That's just 16. But for 3x squared, how can we do that, right? We can just use the constant multiple rule to pull out the 3. Do the same with x cubed. Pull the 5 out. And then use the power rule, or the power law, right? Power limit law, to say that this is the limit of x cubed. And then the limit of x as x goes to 2 squared. So, of course, again, x is a linear function with a graph very close to this, just a lower slope than ax. But you can just plug it in by direct substitution. See that this is 5 times 2 cubed plus 3 times 2 squared. And this was 8 times 2, right? Plus 1. My point is, if you use limit laws, you can just replace x by 2 in a polynomial function, right? And 2 being the point x is approaching. If x were approaching 3, then you replace x by 3. So that's calculating a limit by direct substitution, whatever that is. Let me use my calculator to see what that is. That will be 5 times 8, which is 40, plus 3 times 4 plus 16 plus 1. I believe that will be a 69. So we were able to calculate that limit. And as a general rule, the calculations we did here can be repeated and can be used for any polynomials and rational functions, as long as you check that the denominator of your rational function is not equal to 0. In any other cases, you can just plug in and directly substitute your a value into your expression. As an example, the limit as x approaches 4 of 3x squared minus 5x. What happens if I plug that in? I just get a 3 times 4 squared minus 5 times 4 over 4 times 4 squared minus 36. The bottom will not be 0, because that is a 16 times 4. That's a 64, I think. And I'm always double checking myself. And that will not be 0 when subtracted by 36. So the top will be a 16 times 3, which is a 48, minus a 20 divided by 64 minus 36. So that's a 28 divided by 64 minus 36, which equals 28. So that's just 1, which is great. It's just an easy limit. That's direct substitution. I'll write it down so that you remember the name of this. It's important that you know the name of the technique we're using when you're studying calculus. There are many different techniques, so we have to be able to tell someone which one we used. One bad thing is that we're not allowed to do that for 3, because if you plug in 3, and I'll use the red pen now, if you plug in 3 at the denominator, that would be 3 times, so let's start with the numerator, it's fine, squared minus 5 times 3 divided by 4 times, so 3 squared is 9, 36, so I plugged in 3. The bottom would be 0. And I use quotation marks now because I don't want people reading this thinking that I think I can divide by 0. I'm using quotation marks to tell them that I tried and it kind of didn't work. So the limit, I won't say that the limit does not exist or the limit is undefined. I'll just say that I am not able to calculate this limit at the moment. I'll explain different techniques that you can use to find this limit on separate video. So I hope this was clarifying.